Welcome to the Explainer. All right, today we're seriously leveling up. If you've tinkered with simple 2D robots, get ready, because we're jumping into the deep end with a full 6-degree of freedom industrial arm, the UR5e. We're going to go from the basics to what it really takes to control one of these complex machines. So, here's our roadmap. First, we'll tackle the big challenge of moving from 2D to 3D. Then, we'll get into kinematics to figure out where the arm is. After that, Jacobians to control its speed. Then the real magic, inverse kinematics, which is all about reaching a specific goal. We'll even dive into the physics of it all with dynamics before putting the whole puzzle together to see this incredible robot in action. Okay, so if you've gone through our first lab, you're probably feeling pretty good about those planar arms. But the UR5e, it's a whole different beast. We're in a new dimension of complexity now, and that means we need a whole new set of tools. Let's break it down. We're jumping from a flat 2-joint world to a full 3D space with 6 joints. And that means we're not just tracking a simple XY position anymore. Nope. Now we have to control both where the gripper is and which way it's pointing. Your high school trigonometry, it just won't cut it anymore. We're in the world of matrix math now. So, what's the plan? How do we even begin to tame this thing? The old tricks simply won't work. We need a much more powerful, more systematic way to think about how all 6 of these joints move together in 3D space. Let's start with the absolute most fundamental question. If I tell you the angle of all 6 joints, can you tell me exactly where the end of the arm is and which way it's pointing? This is the core idea behind what we call forward kinematics. And here's why it's so tough. With 6 different joints all rotating in 3D, trying to track everything with basic angles and triangles turns into an absolute nightmare. The axes of rotation are constantly shifting relative to each other. It becomes a chaotic mess, almost impossible to solve by hand. And that's where forward kinematics, or FK, saves the day. It gives us a disciplined, repeatable process. Instead of getting lost in a mess of angles, we use a chain of matrices, one for each joint, to systematically build our way from the robot's base all the way to its gripper. And this is how we do it. The Denevitt-Hartenberg convention is, frankly, brilliant. It lets us describe the geometry between any 2 joints using just these 4 standard parameters. It doesn't matter how complicated the robot is, this framework turns that potential chaos into a nice, structured table of numbers. All right, let's kick it up a notch. Now that we can find the arms pose, the next logical question is, how do we actually control its motion? How do we connect the speed of the motors in the joints to the speed of the gripper out in space? The answer is this incredibly powerful tool called the Jacobian matrix. Think of it as a translator. It answers the question, if I spin my joint motors at these specific speeds, exactly how fast will the tip of the robot move and rotate in the 3D world? It is the absolute key to controlling velocity. But the Jacobian also reveals a fundamental weakness. There are certain poses, certain configurations, where the robot basically gets stuck and loses its ability to move in a particular direction. These bad spots are called singularities. And for the UR5e, there are 3 classic types we really have to watch out for. There's the wrist singularity, which is when 2 of the wrist joints line up perfectly. There's a shoulder singularity, when the wrist is right over the base. And, of course, the elbow singularity, when the arm is stretched all the way out. So how do we know if we're getting close to one of these problem poses? We can actually measure it with a value called manipulability. You can think of it as a score for the robot's dexterity in any given pose. As the robot gets closer and closer to a singularity, this score just collapses towards 0, giving us a clear warning that we're about to lose control. Okay, now we're going to flip the problem completely on its head. So far, we've been figuring out the pose from the joints. But what if we already know the pose we want? How do we find the right joint angles to get there? This is the challenge of inverse kinematics, or IK. It's what you need to solve anytime you say, okay, robot, I want your gripper to be right here, pointing in this direction. It's absolutely essential for pretty much any useful task you can imagine. Now, here's where it gets really clever. There are a few ways to solve IK. The standard method, the pseudo-inverse, it works. But when you get near one of those singularities we just talked about, it can totally freak out and command these huge, jerky movements. That's where damped least squares, or DLS, is a game changer. It adds a tiny damping factor that basically tells the robot to chill out, preventing those crazy movements and keeping the motion stable and smooth, even in a tricky pose. Up to this point, believe it or not, we've only been talking about geometry, just positions and angles. But in the real world, things have mass. Motion requires force. To get this arm to move, we have to apply real torque at the joints. This is where we enter the world of rigid body dynamics. Joints don't just move on their own. We need a physical model of the robot to figure out exactly how much torque each motor needs to generate to fight against gravity, the arm's own weight, and its resistance to starting and stopping. And this is the full equation of motion. I know it looks intimidating, but it's really just like how you move your own arm. The total torque you need, tau, is just a sum of three things. M is for mass and inertia, how hard it is to get things moving. G is the force of gravity you always have to work against. And C, that's the really tricky part. It represents Coriolis forces, those weird effects you feel when something is moving and rotating at the same time.
And you're right, we do not solve that monster by hand. We have a toolkit of incredibly efficient algorithms to do the heavy lifting. First, CRBA calculates the robot's inertia. Then we have RNEA, which solves the most common problem. You tell it the motion you want, and it tells you the exact torques you need. And finally, there's ABA, which does the reverse. You tell it the torques you're applying, and it predicts the motion that's going to happen as a result.
So what happens when we put all these pieces together? Kinematics tells us where we are. The Jacobian tells us how to move. Inverse kinematics tells us how to reach our goal, and dynamics tells us the forces needed to do it. We've built a complete toolkit. With this toolkit, we can build a complete control pipeline. So for a task like drawing a cube, we first use our IK solver to find the joint angles for each corner. Then we generate a smooth path between them. And finally, our dynamics model calculates the perfect torques to follow that path with incredible precision. And the payoff for all this theory? Just look at that number. Incredible precision. By putting everything together, the final demonstration achieves a tracking error of just 88 microns. To put that in perspective, that is thinner than a human hair. And look, this foundation we've built isn't just for drawing cubes with an industrial arm. These are the core principles of modern robotics. They scale all the way up from the factory floor to controlling complex humanoid robots and planetary rovers. The tools are the same, only the challenge changes. What would you build? Thanks for tuning in to this explainer.